All right. So today we'll start our chapter 20 stuff. So basically now we're moving into exam number 4 section. So this is going to be our magnetic field section of this class. So we'll start talking about magnetic field today. So one thing about magnetic fields is magnetic fields unfortunately don't get the love from us that electric fields are going to get. Reason for that is magnetic fields are a little bit harder, so it's a little bit harder to actually talk about the concept. So basically all we're going to do is we're going to compare and contrast it to basically electric fields, kind of say they're basically kind of the same thing, and then just kind of move on and then talk about the differences and how we actually create them, even though there's a lot more subtleties that actually go into it, but we're not going to actually dig into those kind of subtleties. So just notice we're not going to take as much time with magnetic fields as we did with electric fields, because they are fundamentally a little bit more difficult to actually talk about, but that's okay. So when we talk about magnetic fields, as I said, let's basically compare and contrast them then to electric fields. So let's make 2 columns. So let's talk about electric fields here, where electric fields we know are denoted by E, and then we're going to have magnetic fields, where magnetic fields are actually denoted by a B. So a B field is actually what we call a magnetic field. Now, sometimes in literature, of course, you're going to see magnetic fields written other ways. There's also what you're going to see is H. There's also what's known as an H field. The H field is actually what's known as an auxiliary field, which is very similar to a magnetic field, but not exactly quite the same. But if you're dealing with magnetic materials, you're actually dealing with the H field, not the B field. Having said that, all that means is electrical engineers, for example, care more about an H field than they do about a B field. That's basically all really cares about that. But again, they're basically the same idea. So anyways, let's talk about differences between electric fields and magnetic fields. So first, let's talk about, for example, how do we measure an electric field? Or basically, how do we determine the direction of the electric field? So determining the direction. So as we know, going way back to when we first talked about this, the way we determine the direction of the electric field is we simply put in a positive test charge. So we took little q, which was positive, placed this into an electric field, then measured the force, then we knew that the electric field then pointed in the same direction as the force. Right? So then we looked at the direction of the force, and then E and F pointed in the same direction because it was a positive test charge. So F and E point in the same direction. So again, if this was our space, right, so here's my space, we simply dropped in our positive point charge. So here's my positive point charge Q. In this case, if we measure the force, say pointing off in this direction, this was our force F. Then the electric field then pointed in exactly the same direction, but it had bigger magnitude because the size of the charge was very small, right? So this was how we determined the direction of the electric field. For a magnetic field is basically done the same way, except we're not going to use an electrical object, which is what a charge is, to determine the direction of the electric or the magnetic field. We have to use a magnetic object. And the best magnetic object is simply this, a bar magnet. This is what a compass is. So what a compass is actually a bar magnet, which is then held up by torsion, which is allowed to then rotate. Right? So this is basically all we do. So we're going to take a magnetic object, i.e. a compass, and we place that into a magnetic field. And then basically we look at how this thing actually rotates in the direction in which it points. So as this thing starts to rotate and then points in some particular direction, then we say the direction of the magnetic field at that point, and then points in the direction of the north side of the compass. Then the compass needle points in direction of the B field. So all that means then is if this again is my space and I take my compass, so here's my compass, and then my needle, for example, I don't know, say points in this direction. So this is the north side and this is the south side. Then in this case, we know that the direction of the local magnetic field at this point then points in the direction of the north side. So this is our magnetic field. So this is how we determine the direction of a magnetic field. And so we simply take a compass, i.e. a magnetic object, in this case, simply a bar magnet, allow it under torsion to be able to rotate around, and then it points simply in the direction of the local magnetic field. So next thing is what actually then sources electric fields and what sources magnetic fields. So what sources these guys? So what generates these? Well, if we go back, remember, again, when we talked about electrical field stuff, what sources an electric field? If you remember. What sources? Any charged particle, exactly. So any stationary charged particle. Exactly. So stationary charged particle will actually give us an electric field. This is what sources an electric field. Now, again, here we have two different types. We have the PHYS charges. These are our source. And then we have a minus charge, which is then the sinks. So basically, these are what we call monopoles. So what a monopole is the ability to isolate a single charge. So here I can isolate a single positive charge. I can isolate a single negative charge. So I have what are called electric monopoles, right? I have a proton only has positive charge. I have an electron which only has negative charge. I don't need both of them simultaneously. I can have one or the other to create an electric field. When it comes to magnetic fields, it turns out that what actually sources magnetic fields is actually current. So current is actually the source of magnetic field, i.e. moving charges. So it actually sources magnetic fields is moving charges, unlike electric fields, which is stationary charges. Now, what this is going to point out to us, and we'll talk more about this as we actually go along, is there's actually going to be a relationship then between magnetic fields and electric fields, because if an electric field is created by a stationary charge, and a magnetic field is moving by or created by a moving charge, since they're both technically created by charge, just one is created with a static charge, the other one's created with a moving charge, they should somehow be related to each other. But we'll investigate that. And it turns out there's actually more ways to create electric fields. We'll talk about that too, but we'll get there. Brief little interludes of things we're going to learn about. Now, what's different though, when it comes to electric and magnetic, is even though this is sourced by moving charge, we can actually create magnets other ways too by having, again, things like bar magnets. So inside of here, there's technically no moving charges, not in the form that we know of, right? Because what we know of is we would need some sort of battery. We'd hook up a battery, which would then cause a current to move through the system. So in that case, if I had a wire, for example, I would create a magnetic field because I have moving charges moving through that based off the wire. Inside of here, there's technically no actual moving charges. There are actually moving charges because of quantum mechanics and other things, but technically there's no actual moving charges in here. So what I can actually also create, again, a magnetic field using something like this, which is a bar magnet. Now, a bar magnet, unlike these guys, always comes in a dipole fashion. Unlike these guys, which are called monopoles, which again means I can separate a positive charge from a negative charge. But again, I can also source this by using something which is called a bar magnet or a magnetic dipole, which can also generate this magnetic field. Now, again, what's different though, is again, if I think about a bar magnet, so let's say here's my bar magnet. I got a north side here, a south side here. So I get a magnetic field that's going to point in this direction. What happens if I take this bar magnet and I chop it in half? What happens in this case? So I'm going to get something here and I'm going to get something here. Now, by chopping in half, am I isolating the north side? No. So what am I going to create? Two bar magnets now, right? So I'm going to get a north side here and a south side here, and north side then and the south side here. So again, I'm going to create a magnetic field here, smaller. Another magnetic field here, smaller. And what happens if I take this one and chop it in half? Same thing. I'm going to create another bar magnet, north side, south side, another bar magnet, north side, south side. I can do this until infinity, and I will still always end up with a dipole. So what actually happens in magnetism, unlike in electricity, is in electricity, I can create these monopoles I can have a single electric charge being positive. I can have a single electric charge being negative, but I can never have a single north pole in magnetism, or I can never have a single south pole. So I can never separate these two guys into what we call magnetic monopoles. So it turns out in magnetism, magnetic monopoles do not exist. So this is a huge red flag. So magnetic monopoles do not exist. And this is kind of a huge concept in physics. So this is one of the basic things about magnetism is I can't have a single magnetic monopole, which is actually kind of weird because truth be told, a lot of our higher level theories of physics actually end up predicting magnetic monopoles, which is kind of a bad thing because we don't see them in nature. So anybody ever heard of inflation before? Not money inflation that, you know, causes our lives to be horrible at this point in time, but I mean inflation of the universe itself. You understand it? So the idea of inflation actually came about was to actually hide magnetic monopoles. So our original idea was that the universe came from something like a big bang, and then what ends up happening is as the universe then starts to expand and starts to cool, you undergo what are called phase transitions. So a phase transition, just like in thermodynamics, right? So if I went from, say, a solid to a liquid, that ends up being a phase transition. Or if I go the opposite way from a liquid to a solid. Now, what always happens is when you go from one phase to another phase, you get what are called relics. Okay? So for example, best way to think about this is if I have water and I start to boil the water. Right? So if you look inside of the water, when I'm boiling it, you see all these little bubbles of, you know, air that are basically coming out. These are relics. So what you end up with then are relics, which are left over from the previous phase. So what happened then in the early universe is our original theory that predicts that we had for a Big Bang, as the universe expanded and cooled, the universe got big enough, everything cooled down, went to a different phase, or we left over with these relics, and it turns out that the relics were actually magnetic monopoles. These were the relics that were left over. Now, the problem with that, again, is that we haven't seen any magnetic monopoles in nature. So the question is, how do you get rid of them without causing a problem? Because you don't want your theory to be broken, because that's just going to be, you have to start all over again. So how do you get rid of it? Well, the answer was you act like a 2-year-old. So what does your 2-year-old child do when they make a mess? You hide it, right? This is what your 2-year-old does. That's their big plan. You hide it. So the parents don't find it until later. They go, wait, what? It wasn't me. She did it, right? Okay. But anyways, they hide it. So the best way they hid it was actually, this is where inflation came from. The idea was that, well, if we make the universe expand at a huge rapid rate, we can still have magnetic monopoles. But if I say made 10 magnetic monopoles in a universe that was this big, and now I inflate the hell out of the universe, so now it's this big, and I still have 10 magnetic monopoles, what's the likelihood that you're going to find it? Basically 0. Exactly. So this is where inflation actually originally came from. And it originally came from to actually hide the fact that we created magnetic monopoles in our theory, didn't actually find them in nature. So we acted like a 2-year-old and we hid what mess we made, and then we just moved on. This is where inflation actually came from. Of course, it turned out to solve other problems and things like that. So it actually worked out to be pretty well, but this was the original idea of it. But yeah, the point is, after that huge spiel, there are no magnetic monopoles in magnetism, at least nothing that we've ever seen. So great. So now we know the source. So the source is current, i.e. moving charges, and we'll spend some time talking about that. Or again, magnetic dipoles, which are actually created from, again, moving charges, but it's moving charges due to the spin of the actual electrons themselves. So the orbital angular momentum, as well as the spin angular momentum. That's a whole other side effect. So what's next? So let's talk about the type of force. So we know that the electric field gives a force onto charged particles. We also know that magnetic also gives a force, right? And I know that's because if I take two objects here, both of these guys are magnetic. In this case, I can take the two, these guys will attach to each other, creates a force, right? Now we know with electric fields and electric forces, that is a long range force. And it turns out that this guy, I can get this guy to stand up, good, is also a long range force, right? So in this case, they don't have to be in direct contact with each other. to actually create a force between the two. So it turns out that both of these guys are both long-range forces. Now, the only thing we know about force is what does it feel a force of or force on? In this case, an electric field only puts forces onto charged particles. So meaning if there is no charge, there is no electric force. And it turns out that for this guy, it's a little bit more awkward because basically if I had a single charged particle sitting in space, there is no force between a magnetic field and a single charged particle sitting still. Right? So basically there is no force on a stationary charged particle. However, if I move that charged particle, i.e. I give it some sort of velocity, then there is a force. So basically, but there is a force on moving charged particles. So like I said, so this one's a little bit different. So if I had a stationary charged particle sitting still, I brought a magnetic field near it, nothing would actually happen to that charged particle. It would sit there, wouldn't even notice the magnetic field. But as soon as I kick that charged particle, give it some sort of velocity, then there would be a resulting force onto it. Okay, so it has to be a moving charged particle. Okay, so this is basically the difference between the two. So they kind of act very similar to each other. So again, the way that we measure them is simply by taking an electrical object, finding the force on it, and find the direction of the field. Here we take a magnetic object, again, find the torque in this case onto it. From that torque, we then find the direction of the magnetic field. What sources these guys, again, are stationary charged particles. Here, what's actually sourced is moving charged particles. They're both long-range forces, and they both interact with their own type of thing. So again, electric fields will interact with electrical objects, where magnetic fields will interact with magnetic objects. Okay. So for the most part, they're very similar to each other, but not exactly the same. Now, one other thing that's different, let's talk about this, is the type of field, what the field looks like. So what I mean here, so what I mean here is, what does the electric field look like? Well, we know the electric field is sourced by positive charges and has negative charges as sinks. But if I had a simple positive charge in space, the electric field lines would move in straight lines. Right? So for the electric field, the field here is always straight lines. My electric field always is moving in straight lines. So grab an eraser. Picture, I mean, okay, let's say here's a positive charge. We know my electric field lines are just going to point out radially in all directions, but they are always simply straight lines. Magnetic fields, or the magnetic object, is actually different. And what's different about it is it actually always forms closed loops. So what do I mean by that? So again, let's take our bar magnet, just to say the north side, south side. When I said is that the magnetic field will point this way, but that's true but untrue simultaneously. So what the actual magnetic field looks like, and what you guys actually saw from lab, is that this thing actually comes out, curls around, comes back down, and then goes in a closed loop throughout the entire magnet. And then it does the same thing on the other side. So it'll come out, curl around, curl back in, and go all the way through the object. So the magnetic field actually is everywhere, but it always makes closed loops. Oops. So the difference here is that the electric field lines will always create straight lines, or magnetic field will always create closed curves or closed loops. This is what the magnetic field looks like. Right? So this is another huge difference between the two. But other than that, they're very similar to each other. Okay. So cool. So next thing we want to talk about is, as we saw in lab, what actually ends up happening is, since I have current creating a magnetic field, then what that means is if I have current moving through a wire, let's say that current's moving in this direction, what does a magnetic field look like for a straight wire? So let's look at the magnetic field direction of a straight wire. Let's talk about this. Now, some of you I already told in lab how this actually works, and hopefully you kind of gathered from lab how it actually works, but we're going to watch this video just to get a little bit better idea. So basically what's going on here is you have, here is a wire. So you can kind of see the wire here. That's got a curved thing here. And then around here, they have 4 compasses, where at the moment, each compass is pointing in the north direction. Right? So all 4 of these guys are pointing in the north direction. So basically what they're going to do is have no current running through the wire initially. So all of them are pointing in the north direction. And then they're going to turn on the current for the wire, and we're going to see what happens. So then we're going to talk about what actually happens. Okay. So here, just in case you didn't notice, current is off. There. So now current is on. So let's see what actually happened. So what happened here is this one was originally pointing north. Now it has slightly tilted, right? It rotated in the counterclockwise direction. This one was north, but then massively adjusted by about 90 degrees in almost 90 degrees. Also in a counterclockwise rotation. This one is now pointing in this direction, right? So initially it was pointing like this, and then it rotated all the way around. So now it's pointing back here. And this one rotated also counterclockwise to now somewhere between north and east, right? Actually, no, that way, right? The opposite direction. So basically what this tells us then is what? The direction of the magnetic field around this current carrying wire. So in this case, the current is going, say, in this direction. It then creates a closed circle all the way around this actual wire itself. So if I drew that on here, what I would find then is that my magnetic field would end up wrapping in a closed circle around this particular wire. Now, the direction at which the magnetic field curls around the wire is what we're going to call right-hand rule number 1. Right-hand rule number 1. Now, we're going to have 3 right-hand rules overall, okay? Now, first thing about right-hand rules is, which hand do you use? Your right hand, great. So we're not going to use our left hand. We're going to use our right hand. Now, what's going to be great about that is anybody in this class who is left-handed, that means in the middle of the exam, you can write with your left hand and use your right-hand rule at the same time and not have to put your damn pencil down. If you are right-handed, like I think most of us in here are, that means you have to put down your pen or pencil, do this, then pick up and then write from there, okay? Now, one of the things, we're going to go over a lot of these right-hand rules. We'll spend some time going over them because they are important, because everything in magnetism is based off of right-hand rules. No other way to get around it. So we're going to have to understand all these different things. But again, it's called the right-hand rule for a reason. You use your right hand. Good. So how does this work? So right-hand rule number 1, this is dealing with the magnetic field direction of a straight wire. Basically, is I'm going to have 2 steps. Step number 1 is you're going to point your thumb at a 90-degree angle to your hand in the direction of the current. Okay, so your thumb, which is perpendicular to the hand, points in direction of the current. All right, everybody's okay with this? Step number 2, your fingers on your right hand will then curl around in the direction of the magnetic field. All right, so your fingers then curl in direction of the B field. So in this case, since my current is going like this, I put my thumb in the direction of the current. My fingers would then curl around in the direction of the magnetic field. which means in this case, my magnetic field would curl around in this direction. So my magnetic field would be doing this. This is my B field. Okay, let's do a couple more examples. So let's draw, I don't know, one wire here. Do another wire here, another wire here, and I don't know, for funsies, do a wire here. Right? So in the first case, let's say that my current is going, I don't know, downward. That's going to be the direction of my current. For this guy, let's say my current is coming out at you. Okay. So basically, I'm going to draw out at you like this. So imagine that this is the arrowhead of an arrow coming at your forehead. It's coming out. For this one, it's going to go in. So this is the quiver on the back of the arrow, right? So you're watching it go away. So you're safe in this case. And I already drew it that way on that one. So let's draw it this way, just for fun. So all we want to do then is determine the direction of the magnetic field for each one. Right? So again, right hand rule number one says I put my thumb in the direction of the current. In this case, my current is going downward. My fingers curl around in the direction of the magnetic field, which means it's coming out and wrapping around like this. Right? So in this case, my magnetic field is doing that. This is my B field. What about the top middle? What's going to be the direction of the magnetic field there? Good. So in that case, thumb points in this direction. It goes around in the counterclockwise direction. So this is my magnetic field. Good, Jaden. And what about going into the board? Opposite direction, so clockwise. So here my thumb goes here. Fingers curl around in the clockwise direction. So this is my magnetic field. Good. And then what about the last one? That's right. So it comes out from the top and then back in on the bottom. So here it's going to do this. So at this point, my magnetic field is pointing outward. At this point down here, it is pointing inward. So it's doing this, coming out, coming back in down here. So this is what we call right-hand rule number one. So right-hand rule number one is going to tell me the direction of this magnetic field as it then wraps around this particular wire. We'll talk about the spatial dependence of this, how it actually depends on R and all the other factors here in a second, but not that right. Okay, so not too bad. So next thing I want to talk about is, so now we know that's what, if I had a current carrying wire and I put this guy into an external magnetic field, it's now going to feel a force because the current carrying wire is creating its own magnetic field. This is a current carrying wire, right? So in a way. So we know this is moving charges, because again, we talked about this before. This is our cathode ray tube. Our cathode ray tube is what? Creating huge potential difference across here, parallel plate capacitors, stripping off electrons from the gas on the inside, which is causing them to accelerate across, meaning that the charged particles being accelerated. And I know that's because, again, as I brought this in before, if I use my magnet here, I can actually deflect the direction of the beam because it's actually a moving charged particle. If this was purely light, that would not happen. Right? Now, so imagine this is my current carrying straight wire. And what I want to do is put that into an external magnetic field. And we want to do some experiments to find out what happens to this beam. Well, we already know, based off of what I'm doing here, that this thing is actually going to be deflected, i.e. it's going to feel a force. Right? So basically, we want to know from doing an experiment, what is the force on that wire if I put it into an external magnetic field? How can we actually determine this force? So we'll talk about it in words. Hard to actually do, but that's fine. So let's talk about this. So let's talk about the force on a current carrying straight wire in an external magnetic field. So force on a straight wire in an external field. So cool. So let's draw a picture. So let's say here is my wire. And let's say this thing is carrying, again, a current. So this thing has a current of I, which means it's creating a magnetic field. We now know how to determine the direction of that, but I'm not going to care about that too much. And let's do some experiments and see what actually happens. right? So let's say experiment number one, what I'm going to do is I'm going to put the magnetic field parallel to the direction of the current. Okay? So basically all that means is I'm going to have the magnetic field pointing this way or magnetic field pointing this way. It's going to be parallel along the direction of the current, okay? Parallel or anti-parallel. So that's going to be experiment number one, and then we'll talk about what happens. Experiment number two, we're then going to change the direction of the magnetic field. Loud in my ear. Apparently I got an email. And talk about what happens in that case. So for this part, let's say we put the magnetic field somehow perpendicular to the direction of the current. So it's at an angle of, say, theta relative to the current. Okay? So in this case, we have that B then is what? At an angle theta relative to I. Give me that one. Number three, we're going to do is then switch the direction of the current to let it go in a different direction, i.e. the opposite direction. And let's see what happens in that case. So we're going to fix B to be exactly the same way, but in this case, then we're going to run current in the opposite direction. This is going to be 3. So let's rotate the direction of the current. It's okay. Get this out of the way. Number 4, we're going to do is what? Change the length of the wire. So let's say the wire has a length L to it. So we're going to say increase the length of L and then see what happens to the force. And then finally 5, not finally 5, one more after that. So for 5, what we're going to do is we're going to what? Increase the size of the current and see what happens to the force. And then finally, for number 6, what we're going to do is we're going to change the size of the magnetic field. So for example, let's say we increase the size of the magnetic field. So let's now perform these experiments and let's talk about the results of the experiments. So the first experiment, it turns out that if the magnetic field is parallel to the direction of the current or anti-parallel to the direction of the current, this results in actually 0 force. Nothing happens. The wire is not moved, it's not deflected, nothing actually happens to it. Now what happens? So now if I change the magnetic field so it's not parallel anymore, but it is slightly perpendicular to it, what happens in this case then is that the force, magnitude, is no longer equal to 0. So what happens now is that the wire is going to feel a force, it's going to be deflected, and the deflection is actually going to be deflected maximally when the angle is 90 degrees. So when the magnetic field is perpendicular to the direction of the current, this gives us our maximum deflection. So F is equal to F max at theta is equal to 90 degrees. So when these two guys are perpendicular to each other, this will then give us the maximum amount of force. It's okay? Next one, if I change the direction of the current, what actually happens in this case then is the direction of the force changes by 180 degrees. It points in the opposite direction. So here what happens then is that the force goes to negative of the force. So it just switches direction. Number 4, turns out if I increase the size of the wire in the external magnetic field, so meaning if I had more wire, more current carrying wire inside of the external magnetic field, in this case, it turns out that the magnitude of the force also increases. So the size of the force becomes bigger as the length of the wire becomes bigger. Number 5, turns out if I increase the current, the size of the force also increases. So if I run more current through it, I create a larger magnetic field inside of the wire, which then creates a stronger magnetic interaction, which means in this case, the magnitude of the force increases. Finally, if I keep the current the same, but I increase the external magnetic field strength, in that case, the size of the deflection also increases because again, I'm increasing the magnetic interaction. So in this case, the magnitude of the force also increases. So let's use all these things and let's actually talk about then what should the magnitude of the force look like then? So let's talk about each one. So experiment number 1 and experiment number 2 both tell me that the force depends on an angle, but does it depend on the cosine of the angle or the sine of the angle? Does it depend on the cosine or the sine of the angle? Sine of the angle, right? Because this thing is maximal when it's perpendicular. Remember, sine tells me perpendicular, where cosine is parallel, right? So the parallel portion would go to 0. So the perpendicular portion is what's non-zero. So this tells me then my force then must be directly proportional to sine of the angle. Right? 3 we'll come back to later. What does 4 tell me then? So the force is then directly proportional to the length. Right? So in this case, if I increase the length, I also increase the force. I know this guy's going to be proportional to the length. What does number 5 tell me? So the force goes up because the current went up. So how does the force depend on the current? It's proportional to, right? So in this case, I know it's also proportional to the current. And then finally, what does number 6 tell me? It's proportional to. Exactly. So in this case, I know it's also directly proportional to the magnetic field. Great. So if I put all these things together, what this tells me then is that the force on my current carrying straight wire magnitude is then equal to the current times the length times the magnetic field times sine of the angle between the two. Okay, so this is the magnitude of the force on my current carrying straight wire. Now, this part here, number 3, actually tells me that this thing is a cross product. The other way I know it's actually a cross product is because of the sign term here. So if I wrote this as a vector, because remember, force is actually a vector, this is only the magnitude. So if I wrote the force on the current carrying wire as a vector, the way I would write this then would be I times L cross B. So this is actually what we call a cross product. Now, in this case, all this means then is if I change the direction of the current, or if I change the direction of these two, what that does is it flips the direction of the force. This is one of the main things about a cross product. So if I do the order of operations in a different way, I get a different result. All that means is the direction of the force actually changes. But this is actually the force on a current carrying straight wire. Now, you may be wondering why I have a vector sign on the L and not a vector sign on the I, because again, as we talked about, current is actually a scalar quantity, which means even though I gave it a direction, it's not a vectorial direction. But since this is a vector, I have to have the multiplication by a cross product between two vectors to get another vector out of it. So the way we do this is we promote the length of this thing to a vector itself. Okay. Now, the direction of the length vector points in the direction of the current. Okay. But the magnitude of this length vector is equal to the length of the actual wire itself. Right? So if I was going to draw that on here, let's say here is my wire. So in this case, all this means is if my current is flowing in this direction, I, this thing has a length of L to it, then I would say this thing has a vector L, which points in the direction of the current. And this thing then would be in an external magnetic field, this would be B. So this would then be my angle theta, which is the angle relative between the B field and the length, which is the same thing as the direction of the current. Okay. Again, just notation purposes. Ultimately, when I get to this part here, it doesn't really matter. But what I really care about is this angle, again, is the angle between the current and the magnetic field. Even though it's technically a vector here, is going to be this length. But the length, again, will point in the direction of the current. So ultimately, as far as this class is concerned, it doesn't matter that much. Okay? But again, just slight little subtleties here. Okay? Now, this is going to bring up a new right-hand rule. Because now, if we know the direction of the magnetic field, we know the direction of the current, now we need to figure out what's the direction of the force on this wire. This is now what's going to bring up right-hand rule number 2. So let's talk about right-hand rule number 2. So right-hand rule number 2. Now, I'm going to preface right hand number 2 by saying, I'm going to write it in this form. I have a vector A crossed by a vector B is equal to a vector C. We're going to work on this, and then I'll match that to these things over here when the time comes. So the way this is going to work is this is going to be broken up into 3 steps instead of 2 steps. So step number 1, you're going to point your fingers of which hand? Left hand, exactly, into the direction of the first vector, which in this case is vector A. Okay, so first step is to point fingers in direction of A. Okay, step number 1. Step number 2. Then you're going to take those fingers that you pointed and curl them in the direction of the smallest angle towards the second vector B. Okay, so then you curl fingers in direction of smallest angle. And we'll do a bunch of examples of this. Toward that second vector B. Okay, so that's step number 2. Step number 3, then your thumb, which again is at a 90-degree angle to your hand, points in the direction of the final vector, which in this case will be vector C. Okay, so then your thumb, again perpendicular to the hand, points in direction of C. Write this up again here in a second. So let's do a bunch of examples of this just so we can get a good idea of how this thing actually works. Okay. So draw a bunch of different things here. So let's do some easy ones first. So let's say, I don't know, A points in this direction, B points in this direction, and what I want to know is what is the direction of C. Okay. So the way this works is, again, number 1, we're going to point our fingers in the direction of A. So here I would do that. That's direction of A. Okay. Now B then says, or 2 says, to rotate and curl my fingers towards the direction of B. Now, since B is here, that means I'm going to have to rotate my palm towards B in the direction of the smallest angle, where this is the smallest angle, and then curl my fingers towards the direction of B. Okay. So I'm kind of grasping at B. My thumb then, which is at a 90-degree angle to my hand, is now pointing in the direction of C, which means C in this case is pointing into the board. All right. Okay with this? So C then points this way. Okay. Now notice if I did the long angle, it would point in the opposite direction. Okay. Because if I rotated this way in a huge angle, it would point in the opposite direction. Now also notice that the order at which I do the cross product actually matters. And why it matters is, again, because if I did A cross B, so again, I put my fingers in the direction of A, curl towards B, my thumb points into the board. But if I do B cross A, so put my fingers in the direction of B, curl towards A, my thumb actually now points out of the board. So this is where the property of the cross product came from, that number 3, that said it rotated in the opposite direction when I did it, switch the direction of the current. So unlike things like dot products, cross products, the order actually matters. The order of operations here matters because it rotates the vector by 180 degrees. It gives you the absolute wrong direction if you do it in the wrong order. So make sure you get the order correct. Okay. So all that means is that what A cross B is not equal to B cross A, but is in fact equal to negative B cross A. Means that these guys do not commute with each other. This is like saying 3 times 5 is not equal to 5 times 3. 3 times 5 would be 15, but 5 times 3 would be negative 15 in this case. Okay, so the order of operations actually matters. Okay, let's do some more. So let's say in this case, I don't know, A is coming out, B is going down. What's the direction of C? Good, Grant. Good. That way. So C would point this way. How do I know that? Again, A is pointing out, so I put my fingers in that direction. B is downwards, so I turn my fingers down towards B. My thumb then points in the direction of C, which in this case would be to your right. Okay. Let's do another one. Let's say, I don't know, B points off in this direction. Let's say A is going, I already did that, into the board. So here's A. What's the direction then of C? Oh, down this way. Okay. So in this case, A is this way, B is this way, so it's actually down this way. Okay. So this is C. All right. Let's do one more. So let's say A is this way, B is this way. What's the direction of C? Almost. This one's actually a trick question. Technically, or zero directions actually. So in this case, there is no C. C is zero vector because how is A and B aligned with each other? They're anti-parallel to each other, right? So what's sine of 180 degrees? 0, right? So in this case, the result is actually 0. So technically it doesn't exist, or it points everywhere because it's 0 length vector. So this one's actually a trick question. There is no C. That's basically the point of this one. So this is what we call right-hand rule number 2. So right-hand rule number 2 is going to tell us the direction of anything that looks like this. Okay, so anything that has one vector crossed by another vector equal to a third vector, this is the way we determine the direction of that third vector. Now, why is that important? Because again, we're dealing with now something that looks like this. So we now said that the force is then equal to I times L cross B. So in this case, F is equal to C, A is equal to I times L, and B is simply equal to B. So the way we would determine our force then is we'd have to point our fingers in the direction of the length, curl them towards B, and then our thumb gives the direction of the force. So in this case, if this was my current carrying straight wire, carrying current, again, say in this direction, magnetic field is say in this direction, and I want to know what's the direction of the force. Well, again, the way I have to do it is I put my fingers in the direction of the current, curl towards the external magnetic field, so I can rotate my palm like this, curl towards the magnetic field. My thumb gives the direction of the force, which means in this case, this would feel a force into the board. This would be my magnetic force. Okay. So this is the force on a current carrying straight wire. Again, it's giving this way, or magnitude wise, this is equal to I times L times B times sine of the angle, where the angle is specifically the angle between the magnetic field and the current. So this is my angle. Okay. So cool. So this is the force on a current carrying straight wire. So let's use this and let's do an example. So this says we have a rectangular loop of wire hangs vertically in an external magnetic field. A uniform external, where am I? Yeah, a uniform external magnetic field is directed horizontally, perpendicular to the wire, and points towards you at all points. Okay, so let's start drawing our picture. So here's my magnetic field, B, which at every point along here is pointing outward. So here's my B field. And it says that my loop of wire is basically doing something like this. So this is my loop of wire. So the wire itself has current running through it perpendicular to the direction of the magnetic field. Okay, then it says in a portion of the wire that is 10 centimeters long, a downward force is determined to have a magnitude of F, which is equal to 3.48 times 10 to the minus 2 newtons when the wire is carrying a current of 0.245. Okay, so let's say in this portion down here, this thing has a length L, where that length L is equal to 10 centimeters, so 0.1 meters. This thing results in a downward force. My force is pointing in this direction, where the magnitude of the force then is equal to 3.48 and 10 to the minus 2 newtons. And this is carrying a current where the magnitude of the current is equal to 0.245 amps. Cool. So finally, it wants to know what is the direction of the current in the wire and what is the magnitude of the magnetic field. So sorry, notation issues here. That should be a B, not an F, but we'll talk about units of the magnetic field here in a second. It's what we call a Tesla. But so cool. So first, let's talk about the direction of the currents. What has to be the direction of the currents in this case? Remember, our magnetic field is coming outward. So this is our B. Everywhere in the space, it's coming outward. So in this case, it's a little bit different because here we were looking for the direction of F, but now we know F and we know B, and we're trying to use that to figure out the direction of the currents. So how would we figure out the direction of the currents? Almost. What's the direction of the magnetic field though? Coming out towards you, right? So what we want is our thumb to point downward. Right? So we have two options. Either our hand's going to be this way or our hand is going to be this way, right? But our magnetic field is coming which way? Outward, which means I wanted my fingers to curl in the outward direction, which means my fingers have to initially be pointing in this direction. So that means that has to be the direction of my current. So I have to point my fingers in the direction of the current, curl towards the magnetic field. My thumb would give the direction of the force. That means in this case, my current would have to be moving in this direction. So this is my current in this wire. So it has to be pointing to the right. If it was pointing inward, what that means then is that case, I'd have to have my thumb pointing this way, curl my fingers to the inward direction if the magnetic field is pointing into the board, which means my current would actually be going to the left in that case. Because initially my fingers would be to the left. But since it's outward, how do we do that? Okay. So good. So now we know the direction of the current. So now we just have to mathematically find what is the current. So good. So in this case, we know that the magnitude of the magnetic field is equal to the current times the length times magnetic field times sine of the angle between the two. Now, in this case, what is the angle between the current and the magnetic field? Remember, that angle is the angle specifically between the current and the magnetic field. So what's the angle between the current and the magnetic field? 90 degrees. Good. So in this case, my current is going this direction. Magnetic field is outward. So that's a 90-degree angle between the two. So in this case, I know theta is simply equal to 90 degrees. So it's going to be equal to ILB. Good. Here, I know I know L, I know F. So I'm simply going to use this to solve for B. So this says that the magnetic field magnitude then is equal to the magnitude of the force divided by the current times the length. Look at my numbers. What I find in this case then is this works out to be 1.42 times the units of a magnetic field, where the unit of a magnetic field is what's called a Tesla. So the unit of B is what's called a capital T, which is equal to a Tesla. From here, we can then determine the units of Tesla. That's going to actually be a Newton per amp per meter. So Tesla is actually a Newton per amp meter. So this is what we call a Tesla. So Tesla is actually the units of a magnetic field. Now, this, of course, is not the only unit. This is the SI unit. So this is our SI units for magnetic fields. There's alternative units. You can use Gauss and other types of things. They're all, of course, related to each other, but we don't have to worry too much about it. It's okay? Now, what we know is, again, a current is nothing more than a whole group of moving charges, which means that if a current carrying wire feels a force, because it's carrying a current, then that means a single charge should also feel a force. Because if nothing's happening, if a current is just moving through and all the currents is just a bunch of charges moving in a given direction, that means each one of those individual charged particles must actually be feeling a force. So the next thing we want to look at is, well, what is the force then on a single charged particle? So let's talk about that. So what's the force on a single charged particle? force on a single charge particle. Now, to do that, again, I'm going to talk about my wire. So let's say here's my wire. Here's my current. Here's my magnetic field. Here's my angle of theta. Right? Now, again, let's talk about what we just found out. We just found out that the magnetic force on the wire was equal to the current times the length times then the external magnetic field. I'm going to write it as a vector, and then we'll put it in magnitude here in a second. Now, what is the definition of current again? What do we define current to be? Moving charge particle. So it is the change in charge divided by the change in time, right? So in this case, I know the current is simply the same thing as the change in charge divided by the change in time. But since this is a current carrying wire, meaning that all of the charges have exactly the same charge, then it's just simply equal to the number of charged particles times the charge per unit time. Right? So it's going to be the same thing then as the number times the charge, all divided by the change in time. Good. Okay? So what we know is inside of this wire, I have my charge. Here's my charge Q. It's moving, say, in this direction with our drift velocity. So this is our velocity V. And it's going to cover some length during this time of delta t. Right? So it's going to start off here. It's going to end off here. So it's going to cover a length of L in this time frame of delta t. So how would I determine the length of L based off the velocity and time? Remember, this thing's moving with a drift velocity, so it's not accelerating. It has a constant velocity. So how is L related to V and T? Not over T, but times T. Very good. So in this case, I would say L then is equal to the velocity times that same change in time. And a magnetic field is just a magnetic field. So let's put all these things together. So this is then going to be equal then to the number of charges times the charge divided by the change in time, times the velocity times the change in time, all crossed then by the magnetic field. Now, since this time delta t here is the same as this time delta t here, what happens to those two delta t? Cancel, right? So let's get rid of those. So finally, this guy's going to become equal to the number of charge particles times the charge of the particle times the velocity crossed by the external magnetic field. Or let's put some parentheses around this guy. So all this says then is that what? The total force on the wire that has currents moving through it is then equal to this times then the total number of charges that have moved through. Which means that the force on a single charge particle is simply everything inside of this parenthesis. So all this says then is that the force on a charged particle then is equal to the charge of the charged particle times the velocity at which that charged particle is moving, crossed then by the external magnetic field. Or magnitude-wise, this is then going to be equal to the charge times the velocity times the magnetic field times sine of the angle between the two, where in this case, the angle is specifically the angle between the magnetic field and the velocity. This is the angle theta. So again, all this guy says is that if I had a single charge particle moving with a velocity of v in an external magnetic field, this guy may or may not feel a force. It's going to feel a force as long as it's moving somehow perpendicular to the magnetic field, but if it's moving parallel to the magnetic field, it will feel no force. So it has to be moving somehow perpendicular to the magnetic field, hence the sine portion here, to feel a force. The direction of that force, again, is given by right-hand rule number 2. In this case, you point your fingers in the direction of the velocity, curl towards the magnetic field. Your thumb would then give the direction of the force. Okay? Now, there's another caveat that goes on here. The other caveat is what happens if the charge is negative? For example, it's an electron moving in an external magnetic field. What would have to happen in that case? What would happen in that case then is if you do your right hand rule and you get your thumb pointing in, say, some direction that looks like this, because the charge is negative, what does a negative sign do to a vector? flips by 180 degrees. So what's going to happen is if I'm dealing with a negative charge and I get my thumb to point this way for a positive charge, then for the negative charge, the force would have to point in the opposite direction by 180 degrees because I'm multiplying a vector by a negative sign. So the only caveat on this one, which makes it slightly more difficult, is now you have to take into account the sign of the charge. So if the sign of the charge is negative, it's going to rotate the vector by 180 degrees. Or if you really want to confuse yourself, you can then use your left hand. Your left hand is with a negative charge. Your right hand is with a positive charge. Now, if you don't want to confuse yourself, just use your right hand and rotate by an extra 180 degrees. Probably better that way, but you can use your left hand. In that case, it would be the left hand rule number 2 instead of the right hand rule number 2. But again, like okay. So this is the force on a single charge particle. So let's use this and let's do an example. So this says we have an electron which travels at 2 × 10⁷ meters per second in a plane perpendicular to a uniform magnetic field of magnitude 0.01 teslas. We want to determine, what does the electron do? What kind of path does the electron follow in this external magnetic field? So let's talk about this. So let's say here is my charge, or we know our charge is an electron, so it has a charge of -e. And let's say this thing is with a velocity moving in this direction, i.e. in this plane, the plane of the board, and then the magnetic field is perpendicular to that, which means that the magnetic field is either going into the board or out of the board. Which way you want it to go? Preston, which way you want the magnetic field to go? You want to go into the board or out of the board? Out of the board, sweet. So let's say our magnetic field is pointing everywhere out of the board. Here's my B field, draw some representative ones. And etc. Now, what we want to know now is this electron is going to move in some sort of path due to the force which is on it. So we want to know then, what is the path of this electron? All right. So let's talk about that. So let's do this. So first things first, let's determine the direction of the force, and then from the force, we'll try to figure out a pattern and then figure out what the path is of the pattern from there. So okay, what this thing says is we're going to point our fingers in the direction of the velocity, curl towards the magnetic field. Our thumb will then give the direction of the force, but since this is a negative charge, we'll have to rotate by an extra 180 degrees. So let's do that. So in this case, I point my fingers in the direction of velocity. Velocity is this way. Which way is the magnetic field? Out of the board. So we're going to rotate then, put our thumb in the direction of that guy. Well, you're using your left hand, so you don't need to rotate. There you go. So in that case, my palm's going to be towards you guys. I'm going to curl towards, and my thumb's going to give the direction of the force, which means the force should be down. But since this is a negative charge, I then have to rotate by an extra 180 degrees, which means the force is going to be upward. So this is going to be my force at this point. So at this point, my force will be upward. Those will be my magnetic force. Okay. So what's that going to do? So what that's going to do is the force then will be perpendicular to the velocity, which means what should happen to this guy as it moves? Watch your head, Sam. So I have this guy, I get a velocity in this direction. What's going to be the direction of the force? Perpendicular. So what does it do? It started the curve, right? So it's going to start the curve in the direction of the force. So this force is going to pull it in that direction. So this thing is going to end up doing something like this, right? It's going to move up to say this point. So let's look at this point and see what's happening here. So at this point, the velocity now is pointing in this direction. This is my velocity v. Now let's find the force at this point. So in this case, I again put my fingers in the direction of the velocity, like this way. Curl towards the external magnetic field. So I got to rotate my palm outward, curl this way. But again, it's a negative charge, so then I got to curl back in this direction. So my force now is going to point this way, again, perpendicular to the direction of the velocity. So this is now the direction of my force. What's that going to do? It's going to curve it more, right? So now it's going to move to say this position here, right? So now let's look at this position. So this position, my velocity now is pointing, say, in this direction. So again, I would do the same thing. Put my fingers in the direction of the velocity, curl towards the magnetic field. So I get this. But again, it's a negative charge. I got to rotate backwards in. So this guy now points in this direction. So this is the direction of my force, and etc. So what is happening to this electron in this problem? It's going to go in a complete circle. Exactly. This thing is actually going to do this. It's going to rotate in a circle of some radius of r. Now, we think back to 175. What's happening here is your force is always perpendicular to the direction of the velocity, which means what's the direction of the acceleration? Also perpendicular to the direction of the velocity. Now, is that going to change the magnitude of the velocity? So if my acceleration is always perpendicular to the direction of the motion, will it change the velocity? No, it changes the direction, but it won't change the velocity, right? So this thing has an acceleration, which is always pointing towards the center. What type of acceleration is that called? Centripetal or uniform circular motion. So what's happening in this problem is as long as the velocity vector is perpendicular to the direction of the external magnetic field, this electron will always end up going under uniform circular motion. This thing is just going to spin in a circle. The direction of the velocity in this case will be pointing in the counterclockwise direction. Now, quick question. If this was a positive charge, say a proton, what would that one do? Exactly, it's spin in the opposite direction, in a clockwise direction. Instead of going up, it would actually go down. Right? This is what this guy would do. So as long as the velocity is perpendicular to the direction of the magnetic field, the motion of this charged particle is always going to be uniform circular motion, which means the velocity will always be the same. It's going to feel a centripetal acceleration towards the center. Now, what we want to know then is what is the radius of this circle? So let's find out. What is my radius of the circle? Well, we know this is going uniform circular motion, which means if we use Newton's second law, we can then say the sum of the forces acting on my charged particle is then equal to the mass times the centripetal acceleration. Now remember, our centripetal acceleration is the velocity squared divided by the radius. This is our centripetal acceleration. Now in this case, the only force which is acting on this guy is the magnetic force. That's the only thing that's happening. So here, the sum of my forces is simply going to be my magnetic force is equal to the mass times the velocity squared divided by the radius. Now we now know that since this is a magnetic force on a single charged particle, this is going to be the charge of the charged particle, which is just the fundamental charge, times the velocity times the magnetic field times sine of the angle between those two times the mass times velocity squared divided by the radius. Now, in this case, no matter where the electron is in its orbits going around through a circle, how is the velocity relative to the external magnetic field? So my magnetic field is doing this. My velocity is doing this. What's the angle between these two things? 90 degrees. So at all points, this angle here is simply going to be 90 degrees. So this is then just going to be EVB is equal to MV squared over R. This V here is the same as this. I'm going to cancel out one of those on the right-hand side. And finally, let's solve for the radius. So this tells me my radius then is going to be equal to the mass times the velocity divided by the charge times the magnetic field. So this is my radius. Something we'll want to keep in our bag of tricks. Okay. From here, I plug in my numbers. I know the mass. This is an electron, so that's 9.11 times 10 to the minus 31. The velocity is what, 2 times 10 to the 7th. The charge is 1.602 times 10 to the minus 19. The magnetic field is 0.01 Teslas. Plug in my numbers. What I find is this works out to be about 1.1 centimeters. So the radius of this circle would be about 1.1 centimeters. Be the radius of this circle. Now, all this means is that my electron moving in an external magnetic field will simply do this. Uniform circular motion. Now, since this is doing uniform circular motion, we can also define all kinds of other things. Remember from 175, we can talk about the period. Remember, the period is the amount of time it takes for this guy to go through one circle. And we can also define the frequency, which is 1 over the period. So let's talk about those things. So this thing, since it has uniform circular motion, will then have a period. The period associated with this, t, is equal to the period. So how do we get the period? Well, again, the period comes from the fact that we know the length of the circle is going to be 2 pi r, is then equal to the velocity times the time. Okay, so this tells me that my period then is going to be what? 2 pi r divided by the velocity. Now, from here, I can then replace the r with mv over eb. So let's go ahead and do that. So it's then going to be 2 pi over v times mv over eb. Okay? With all my shenanigans here. Okay. So this v is the same as this v, so let's cancel those. So this is going to be the same thing as the period then is equal to 2 pi times the mass divided by the charge times the magnetic field strength. So this is what we call the period. So this is the period of oscillation for a charged particle moving perpendicular to a magnetic field. But again, the frequency is equal to 1 over the period, which is then going to be equal to the charge times the magnetic field strength, all divided by 2 pi times the mass. So this is what we call the frequency, where this frequency has a special name. This is what's known as the cyclotron frequency. So old particle accelerators were actually called cyclotrons. With those words, it was basically a magnetic field. You put a charged particle in between and you cause it to spin around in a circle. As it spun around in a circle, it turns out, we'll talk more about this later, that as an object accelerates, it actually gives off light. Kind of cool. So basically what they would do is they would collect the light, the radiation, which is given off due to accelerating this electron in a circle, because again, even though the velocity is not changing, but since it's changing direction, it means it's accelerating all the time, so it's giving off radiation. So this was where originally radiation actually came from. Now, this also plays into other things as well, and this was something we actually talked about a little while ago, but I'm going to talk about it again now, is if you go up north and you look at pretty lights called the Aurora Borealis, that's all this is. So the Aurora Borealis, these beautiful lights here, the northern lights, these beautiful lights around here, is actually charged particles caught up in the Earth's magnetic field, because here's my Earth. Here's the Earth's magnetic field. And as we talked about, when we have solar winds, those solar winds send a whole bunch of particles, which then come in and then start to wrap around the actual magnetic field itself. Now, what happens then is if I had a particle moving, say with a velocity like this, and my magnetic field is like this, what actually happens in this case then is the perpendicular portion of the velocity causes this thing to move in a circle around the magnetic field. The parallel piece of velocity in the direction of the magnetic field doesn't feel the force, which means it just carries along with exactly the same velocity in the parallel direction, causing this thing to move in a helical shape. Okay. Now, as this thing is moving in a helical shape, it has a particular period, or more importantly, a cyclotron frequency, which means it's actually radiating away energy all the time. But why you see it the most around the poles is, again, as we talked about before, the strength of the magnetic field around the poles is actually much, much bigger, because the density of the field lines is much bigger. So what happens is, as it gets closer and closer and closer to the poles, the size of the magnetic field increases, which means the frequency at which this is giving off, i.e. the energy at which the electron is radiating off, also increases. Eventually what happens then is that it gives off enough energy due to this radiation, the cyclotron frequency, to then ionize the air around the magnetic field line. So what you're actually seeing here is the ionization of the air, i.e. the electrons in the air being stripped off due to the radiation, and then being recombined back into the air, which is giving off the green color light. Okay. This is the Aurora Borealis. Simply charged particles in an external magnetic field rotating in a circle. That's it. But it looks beautiful. We'll talk about some other things tomorrow. We'll talk about how we actually discovered the electron, which actually it turned out if you were alive after this class in like 1890, you would have won a Nobel Prize. how easy it was to actually find it if you actually understood the physics. But the physics is this level of how you actually need, and you could have would enough over. Millionaires now, I know, gotta be a little older. So I'll see everybody in lab in a little bit. So today we're going to do an optics lab. Okay. Oh, one more after this one. One more after this one. I haven't posted yet. Yeah, I'll post that one over the weekend. So this is the last one. It's on Blackboard, but yeah, we have one actual lab next week.